Hello, everybody, and welcome to the second exams drug delivery video. I'm sorry it's a little bit later than usual. With biostats and everything else going on this week, it's a little bit harder to get through this content, especially because I know Dr. Lee was going a little bit behind. He didn't really finish until Wednesday. So I have everything here now, though, and I think just judging based on the number of slides I have to go through, this is going to be kind of a longer video, so I do apologize for that. But with that, let's just get into it. So Dr. Desai had a little bit of content left before he turned things over to Dr. Garrett. I believe he only had about 2 lectures, so I'm going to do a little bit of his calculations because I think that'll be a bigger portion of this exam, at least from his content. I don't think it'll be that many questions. But the other thing he touched on was kind of some bioavailability properties, and I think they can be summed up really well with these tables. Um, I don't think all of these tables are necessary to memorize, at least that's what I'm kind of banking on. So I circle the things that I think we will be tested on, or at least could be tested on. Um, so just going through it, it's really important to remember this was a question on our first quiz, and I think it was even a question on the exam. I don't know if they'll repeat it for that reason, but it's IV is the only dosage form with 100% of bioavailability. Um, and you might be wondering why only IV. It's because even with IM and subcutaneous, since those aren't directly in the blood, right? Some of the tissue or some of the drug will stick around in those tissues instead of diffusing completely into the blood, even if a lot of them will get into the blood. And this can be like an advantage or a disadvantage, right? For something like a GLP, we're kind of trying to get systemic. It's not really an advantage, but if we wanted something more localized, like let's say an immunization. We obviously don't really need that to spread the whole body and just make us feel worse. We just kind of need it in a certain area to get those antibodies. That would be a benefit in this case. Another thing to mention is for rectal, buccal, and sublingual, there is no first pass effect. With oral, there obviously is. First pass effect, if you recall from the first exam, is the amount of drug that will be kind of metabolized before it enters systemic circulation. And that's just due to passing through the liver. Um, Oral, despite having these bioavailability issues, is the safest and easiest, and generally the cheapest. Just in the fact that you don't need to prepare it sterilely, like something like an injection. But this obviously has variable bioavailability, so that can be problematic for certain drugs. And when it is a problem, it might be dosed multiple times daily. Take something like hydralazine, for example. That's a 3 times daily drug, which is really good for what it does, and it's great that it's oral, but it's not ideal that a patient needs to take this right when they wake up in the middle of the day and then right before they go to bed. Um, and then as far as transdermal and inhalation routes, um, transdermal delivery, which we'll talk about a lot more in this video, it prefers lipophilic drugs and smaller drugs generally, and we'll get way more into that. And then as far as inhaled goes, these are good for things that are like need to be delivered to the respiratory tract. So for example, like if we were gonna have a beta 2 agonist, at least for something like asthma COPD, we'd only want it in the lungs. And while that does have vasodilatory properties elsewhere in the body, let's say we already have like a hypotensive patient, that's obviously not ideal. So it's really nice that those are selective in the bronchi. Um, and then also for inhaled drugs, they may have those side effects of if they're not like asthma COPD adjacent drugs, they could worsen like a cough or have some reactions. An example of this would be like the inhaled insulin. You generally don't want to use that in COPD, just for the fact that you're kind of putting things in your lungs that shouldn't be there. So next up, I'm going to talk about some more factors that will kind of affect drug absorption. So the 2 main ones that I think you should remember are size and solubility. And like a subsection of solubility is I would probably also think about lipophilicity and pKa, right? Just in the fact that if these drugs are weak acids or bases, they won't absorb as well as in their ionic forms. Um, and so these are 2 really big factors. In lipophilicity, obviously, drugs tend to prefer to be absorbed lipophilically. We'll talk a little bit more about that in transdermal, some exceptions to that. But just as far as oral drug delivery goes, just remember that you'll pretty much always have it right, because I really doubt they ask us an exception to that. Along with going with pKa, stomach and intestine pHs can obviously change where a drug's absorbed. And if you are sick or something, this pH may vary. The amount of time it takes a drug to pass through the intestines, if it takes longer for the drug to, let's say it's starting in the small intestine, it'll have more time to absorb. And through that, you'll have more absorption. Gastric emptying as well. This is kind of variable because most drugs are basic, right? Meaning they will not be absorbed in the stomach. But if it's an acidic drug, delayed gastric emptying will actually probably raise systemic concentrations in most cases because it can actually have more time to cross into the blood in the only area it really can cross into the blood. And then another one that's kind of common sense is the food we consume may benefit or may lower absorption. You all know by this point, it varies drug to drug. Not super important, just depends on how the drug absorbs. Next up, what I want to talk about is this graph. I think we very likely could see something like this, and I want to explain it to the best of my ability. These are essentially, it's measuring peak plasma concentration, right? So what does that really mean? It's essentially how much of the drug is getting into the blood over a certain amount of time. And then right here, we have the three sections of the GI tract. We have the stomach, which is represented by the circles. We have the jejunum, which is shown by the triangles, and the cecum, which are squares. And something I want to mention, I personally don't know this anatomy. I had to look it up. These are in chronological order from the GI tract, like top down. So stomach first, jejunum, then cecum. So using something like this, we can actually predict where a drug is going to absorb. And how do we do that? Or at least where it's primarily absorbed. You think of it chronologically. And I'm assuming if we saw an example like this on the exam, we would be given the chronological order, or at least it would be this exact same chart, implying its chronological order. So you can see here, the difference between the jejunum and the cecum, it's really large, right? Amount of absorption. I'm just drawing a random arbitrary time point here. The difference between the stomach and the jejunum, however, is a lot smaller. So from this, we can kind of use logic to extrapolate where this is primarily absorbed. Does the stomach have the highest absorption? Yes, it does. However, the stomach is not the primary site of absorption of this drug. What you deem the primary site of absorption is where the biggest drop-off is. So you can see here, it's like, sure, there is absorption in the stomach, and it is the most, but you have to keep in mind, since the stomach is moving top down, a little bit gets absorbed in the stomach, and then the rest of it gets absorbed in the other components. However, once you're in the jejunum, once you move to the cecum, and if you were only to do the cecum, which would be the here to here, the time is so much smaller. So we can see the section in between where the jejunum starts and ends actually has the biggest absorption, meaning this drug absorbs primarily in the jejunum, which kind of makes sense, right? It's a part of the small intestine. Most drugs are basic and are absorbed there. So I think if we have access to paper, draw this out. Whatever the biggest section is, the top of that section is going to be what area you absorb in. So again, that's the jejunum, just because it has that biggest kind of difference right there. I hope that makes sense. So next, let's talk a little bit about some of the anatomy of the digestive tract, and really all you kind of need to know is the lumen is this outer top layer, right? This is where our site of absorption is going to be. And what makes up that lumen in the small intestine, because that's what this area is these things called villi. These are kind of like little finger-like projections. They have like some microfilaments, some proteins in them, but they're essentially, I mean, they're on a cell, so they're alive, right? But they don't really do anything. What they do is they're simply there to exist to increase surface area. They don't really move. They don't, well, actually, that's not true. They can kind of move, but that's primarily peristalsis. That's contraction of muscles in the small intestines that'll do that. The villi are just there to absorb. And this is how we get food in our body. This is how we get drugs in our bodies. And then from there, externally to these villi, we have these systems of veins and arteries. And these will all lead from the intestines back into the hepatic vein. And what the hepatic vein will do is it'll bring things, food, drugs, anything that's absorbed in the small intestine through the liver to be metabolized, which is why your first pass effect occurs. So that might be a question. When it is the first pass effect, it's drugs moving from the intestine, very usually the small intestine, to the hepatic portal vein to be metabolized. So that's how drugs get kind of into our blood. One last thing I want to kind of talk about is bile cycles of the stomach. I kind of doubt we see this, to be honest. But in case we do, the stomach will actually, even when there's not food, kind of secrete mucus and bile in intervals. In these intervals, a total one is about 2 hours, right? And they'll be faster if we've eaten something, because the stomach will try and move something along. Uh, but let's say we take a drug orally, right? Needs to be absorbed in the small intestine to be activated. Let's say it doesn't absorb at all in the stomach. If we timed that wrong, it could potentially be 2 hours until a person sees an effect from that drug because it just won't move into the small intestine if there's nothing in the stomach. And granted, we have ways to like speed this up, but that's why you'll pretty much never see an oral drug with like in if it's really well absorbed in the small intestine, with an administration like effect time greater than 2 hours, just because as long as it's absorbed really well when it gets to the small intestine, the longest it would take to move from the stomach to small intestine is 2 hours. And again, food can vary that a little bit, but just kind of a general rule. But again, I doubt we see that. So next up, I'm just going to talk about some just some drugs and how they may vary their absorption based on other factors. Um, we learned a bit about this when we did our ID top 200. Tetracyclines will form complexes, or chelate is another word for it, when they reach positively charged ions. So think your calciums, your aluminums, their magnesiums. These will cause complexes and lower absorption. We have cholestyramine. This is a bile acid sequestrant. This will limit digoxin absorption because they will kind of form a complex, or um, it'll lower absorption essentially, and that's through that complexation. So similar almost to this one. Just usually when we think of complexation, we think of something with like a smaller ion or a smaller entity. Um, Oxidation with cyclosporin. There are enzymes in the stomach and small intestine, like CYP enzymes, phase 2 enzymes, just obviously not as many as in the liver. Um, so drugs may just be deactivated by the stomach or the small intestines, which just happens, and it's unfortunate. But the concentration is so much less. It's not usually something we worry a ton about. Um, Conjugation, reduction, hydrolysis, kind of all the same thing, right? You have your phase 1 reactions, which is talk about that in a second. Your oxidation, your reduction, your hydrolysis, and conjugation is usually a phase 2 reaction. Um, this is a really good concept, I think. Bioavailability is not always the same as liver bioavailability. And part of the reason for that, right, is let's say we have a dose of 100 milligrams. Um, and let's say we know the liver inactivates 75% of that drug. The amount we get in our blood may not be 25 milligrams at that rate. It will most likely be something different. And that's because sometimes our body just doesn't absorb the entire drug. You can see here that 20 milligrams kind of like flowed out, just passed through our intestinal tract. So once we get into the actual blood, we only have 80. Then once we do that 75% of 80, which is metabolized, we only have 20 milligrams left instead of 25. And as you know, those aren't equal. So that's a really good question. We might have a question about that, although I'd assume we'd probably have it with a picture, which would also kind of make it easy. So we'll see, but I think that could be asked potentially. Um, so next up is the way a drug is kind of absorbed. It's based on two factors, and these factors are gastric emptying, it's a T in there, emptying rate, as well as max concentration of a drug. And with these, we can kind of do some PK models to sort of guesstimate how fast they go. So we have here an elimination graph, or no, I'm sorry, the red is the absorption graph, and the green is our elimination graph. And we'll do some math with this on the next slide. But you can see here, just while we have this visual up, that they form kind of this equilibrium. And this is like when absorption is equal to the elimination rate, which is ideal. This is the equilibrium our body will reach. And then once they are the same line, it'll just go until, reaches 0 or whatever. And that's when the drug is completely eliminated from the body. Okay, so let's do some math with extravascular PK. We have 3 forms of gabapentin. We have this IV form, which 200 milligrams was given. we have an oral form where 900 milligrams were given, and we have another oral form where 3,600 milligrams were given. So this first problem wants us to find the absorption and elimination rate constants. So how do we do that? So elimination rate constant should be the same for all of these. In the IV, it's this negative 0.11. In the 3,600, it's this negative 0.11. And even though it's not exactly the same in the low dose oral, it's close enough. It's that negative 0.109. So we're just going to say it's negative 0.11. So for half-life, if you remember, because we just found the rate constants, it's pretty simple. The half-life equation, if you recall, is 0.693. That's the natural log of 0.5, but at this point it's kind of just a number we have memorized, and I think it's even just given on our exam sheets, our equation sheets. So if we do that divided by 0.11, we will get 6.3, and this is 6.3 hours. That's the elimination half-life. Elim half-life. And so now for the absorption half-life. Something you'll notice is this absorption rate constant is not the same as this absorption rate constant. That's not normal. Problem 3 will kind of get into why this occurs. But because of this, we have two absorption half-lives. So same process, 0.693 divided by, we'll do low dose first, that's 0.866, this number right here. 693 divided by 0.866, we get 0.8 hours. And then for this second one right here, similar process, I'm not going to write it out, 0.693 divided by 0.62, and we get 1.1 hours. So nice, we found the rate constants, we find the hours, that's how we do that. Now for the, alright, sorry about that, my recording cut out and it deleted all my work, so bear with me. Absorption rate constants, right, elimination. Okay, boom, up to speed. For this next one, it wants us to determine bioavailability. How do we do that? So if you recall that IV dosage forms are assumed to have 100% bioavailability. So we'll kind of be using that as our denominator to rank our bioavailability, because if you remember, part over whole, our oral bioavailability over our IV will give us essentially what the estimated oral bioavailability is. So what's the math behind this? So what we'd have to do first is we can find our IV bioavailability. And that's really simple to do. First, we need to find its area under the curve. So AUC equals our 2.6, which is our C naught, it's this value right here, divided by 0.11, our elimination rate constant. If we were to do that, we would get 2.6 divided by 0.11, 23.6. I believe this is in micrograms, milliliters per hour. Don't quote me on that, because I'm really bad with the units on these. But it's something like that. It's some obscure unit. It'll just eventually, bioavailability itself is unitless, so it doesn't really matter for this problem what our units are. AUC for oral is a little bit different, especially when there's an elimination and a absorption rate constant. Their AUC is equivalent to their C naught over their K elimination minus C naught divided by K absorption. And if you were to distribute this out, just be careful. It would come out to something like C naught times 1 over KE minus KA. Not like, you know, so if you're going to do that algebra, just be careful. I'll just write it out the long way here just to avoid confusion. We'll start with our low dose. So we have our 8.67 divided by 0.11 minus 8.67 divided by, I think that's 0.866. Yeah. So let me do that in my calculator. 0.867 divided by 0.11 minus 8.67 divided by 0.866. With that, we get 68.8. Let's do it again for our high dose oral. C naught is 16.95 divided by same elimination constant 0.11 minus 16.95 divided by 0.62. Is this the absorption constant? Because remember, those absorption constants are different. So 16.95 divided by 0.11 minus 16.95 divided by 0.62. This we get 126.7. So I'm going to erase all of this really quick because we're still not done. We'll keep those numbers on there just because we'll need them here in a second. So to get bioavailability, which is denoted as F, we can use our oral AUC, which is what we just calculated, divided by the dose over IV AUC, which that was the first thing we calculated, also divided by the dose. So if you remember, the dose of IV was 200, dose of this one was 900, dose of this one was 3600. So I'll write all that out really quick. 68.8 our oral AUC, our low dose oral AUC, divided by 900 over 23.6 divided by 200. Put that in my calculator. For that, we get 0.64. That's linked to this one. The only reason I say that is because I'm about to erase half of this. Same process for this next one. We do our high dose oral bioavailability, which is 126.7 times, or divided by, 3600 divided by 23.6 over 200. 6.7 divided by 3600 divided by 23.6 divided by 200. And for this one, we get 0.29. So these are essentially the bioavailabilities. You can see that the low dose has 64% bioavailability, right? If we were to multiply that by 100, this one only has 29%, which is kind of weird, right? Why would a higher dose of a drug have a lower bioavailability? Something important to remember here, and this will kind of be the premise of problem 3, is that even if something has a lower bioavailability, more of the drug might still be delivered, which is what we see here, right? We can see the C naught is higher in the 3600, so even though the bioavailability is lower, we are probably still delivering more drug, but not at the same rate, so it's tapering off. So if you remember back to our kind of administration of drugs, like linear PK, usually drug administration will look like this. What we have right now is it's still going up, but it's tapering off like this, right? We're not getting the same bang for our buck that we were. We have diminishing returns. And what do those look like, for example? If we have this 0.29 over 0.64, we can see that the efficacy, at least comparatively, is only about 0.29 divided by 0.64. It's only about 45%, right, at this dose compared to like what we would expect it to be on this linear model. So at this point, this is like really high up there. This essentially like doubles where this is at on terms of height on the curve. And why is this? Essentially, if something like gabapentin needs to be moved through a transporter, it doesn't diffuse on its own, right? It'd need a protein pathway, but these could be saturated, because it can only move so much gabapentin. So if this is saturated, we can't move it as fast, and that means we have less where we expect it to, where we're measuring it essentially. It kind of caps out at a certain point. Over time, yeah, it'll get where it needs to go, but there's also processes like elimination going on in the body, all these other factors. So that's why, even though we have this much higher dose and even a higher concentration, the bioavailability is so much worse. So I hope that all makes sense. Okay, so now let's talk about phase one, phase two, just enzymatic metabolism, reactions, things of that nature. We've seen this a lot before at this point. I think a lot of this should be review. Phase one reactions will generally occur first in most cases, although technically phase two can occur first just if a substance encounters that enzyme first, or if it already it's already functionalized. And that's a word we're going to see a lot is functionalization. Uh, Not 100% sure what it means, so don't quote me on this next part, but I believe, wow, that's a long word. Oh, because I'm writing the same thing twice. It's been a long day. I'm losing my mind. Um, what it means is it's making a compound more hydrophilic through there's three types of reactions we can do with a functionalization. We have hydrolysis, which is breaking a bond using a water molecule, and it will result in protonating something and also hydroxylating something. We have oxidation, and this can literally be attaching an oxygen, or it just means we are kind of, I believe the Gen Chem exact definition is we are lowering the base energy state of the molecule through its numbering of bonds, and reduction is the opposite. We're essentially adding a reducing group, not an oxygen, but we're essentially increasing the base state. And when I say those energy states, it essentially means the amount of charge on that molecule. So oxidation will lower the base charge on the molecule because when you're adding an oxidizing group, it will pull electrons away from that atom. If you're reducing something, you're pushing electrons toward it. And since electrons are negative, you kind of flip it, right? So pushing negative in, lower charge, pulling electrons away, higher charge. That's the best way I can explain it. That's not important for this class. What is important is those three reactions. So if it's hydrolysis, reduction, or oxidation, uh, it's automatically phase one. And then phase two are conjugation reactions. These are reactions where you'll essentially like tack something on, right? Like a glucuronide, a glutathione, a sulfur, something like that. Just these really big, generally hydrophilic molecules. And I'll talk about the exceptions in a bit. Um, so when we're metabolizing an enzyme, right, there's a ton of paths we can take, or metabolizing a substance with an enzyme. Um, Acetaminophen is one we've seen a few times now. Um, if we conjugate with a glucuronide, uh, it's non-toxic, same with a sulfate. But if we do it with CYP2E1, we get this compound, I think it's, oh, I forget what NAPK is, but essentially what it is it has a very long name for one, and the other thing is it's very toxic to our body. But luckily, what we can do is we actually have glutathione, which is another phase two enzyme, which can conjugate this again to create a non-toxic product. So you can see there that there can be multiple phase two reactions. Or I guess this is technically a phase one reaction right here, but there can be multiple phase two reactions, just for your reference. And those can potentially toxify, detoxify. There's a ton that can happen, right? Because these enzymes aren't really smart. They don't know what they're doing. They just kind of interact with something and they're floating around in our body. So a lot of things that can happen, a lot of variance there. But generally, we will try and design drugs so they don't become toxic. That's kind of our goal. As far as factors that can change genetics, I mean, this is all going back to MMP, race, age, gender, genetic makeup, so many other factors, drug use, just epigenetics, all these things over time can change how much you might express an enzyme or suppress an enzyme. Um, yeah, not super important for this, just know it exists. Let's move into CYP enzymes. So there's 57 like classes of CYP enzymes. Um, and there are um, three things essentially a CYP enzyme will need. Well, two, but I'll specify the two and a half here in a second. So what we need is we need NADPH. This is a cofactor. This is an energy carrying molecule. If you might remember from MMP, this is something you generate in the pentose phosphate pathway. Again, won't need to know that for this, but just kind of like that's where this comes from in the body. The other thing is an enzyme, a coenzyme called P450 reductase. And what this coenzyme needs to work is this coenzyme also has a cofactor, as if it wasn't convoluted enough. It has a heme molecule. And if you remember, heme is an iron-containing molecule. So whenever there's a CYP reaction, there's always iron involved. And that's if you've ever looked at the mechanism of like a CYP enzyme, you can see there's a lot of kind of changing the charge on that iron molecule, on that iron atom, I should say, in order to catalyze these reactions. So be aware of that. We'll probably see that. This was stressed pretty heavily in class. Um, as you know, there are certain foods that can inhibit induced CYP enzymes. Um, I think the one we're most familiar with is grapefruit juice. Is a CYP3A4 inhibitor. Dr. Garrett also talked a little bit about in class broccoli being a CYP1A2 inhibitor. That was a little new to me. When I usually think of 1A2 inhibitors, I think of caffeine and nicotine, but to each their own, I guess. So broccoli is also a new one. And then for CYP3A4 inducers, we have St. John's wort is the big one I can think of, at least that patients would be exposed to. That's like not a drug. So just be aware of those things in practice. But you know, it's like they're pretty easy to identify, and even then, it's not like the end of the world per se. Just something that could change concentrations, and for something like warfarin especially, we just want to monitor that kind of closely. Um, Another thing is enzymes are not expressed the same. As you know, CYP3A4 is one of the more prevalent CYP enzymes in our body. It also metabolizes a lot. But then you have enzymes like CYP2D6, which metabolize about a quarter of the drugs, right? This really small percentage that looks less than 5% to me. I don't know. I can't really estimate pie graphs. But yeah, way more activity. And just for your reference and your learning, CYP2D6 enzymes will usually metabolize things like pain meds, also some psych meds. Um, so yeah, that's just kind of a fun fact. We might not see them on like the exam, but just something to be aware of. Okay, so that was like everything on CYP enzymes. Another type of kind of phase one reactions, yeah, these are generally phase one, I'd say, because they're oxidation reactions. Are these human flavin monooxygenases. Uh, these are a lot simpler, right? If you remember, CYP had 57 classes of their enzymes. FMOs only have 5. Um, Two really important things. This will be a question. I would be shocked if this was not a question. So these are oxygenases, so they oxidize. Their cofactor is FAD. This was also something that we've seen in like the TCA cycle. It just pops up in various places. But the only two things that can oxidize are nitrogens and sulfurs. Only two things. Only these. And like the way you can kind of remember it is while CYP will usually work on things like carbons, although it can also metabolize nitrogen and sulfurs. That's something else. So CYP can also do this. I think that was actually one of the questions on the quiz, showed an oxidation of like a sulfur. And you needed to be able to recognize that it can do both actually. But if it's something other than a sulfur and nitrogen that's being oxidized, it's CYP. So again, these are way simpler than CYP, a lot less reactions, a lot less substrates, but just good to know. So next up, let's talk about our phase 2 reactions. Those were all our phase 1 enzymes and reactions. The most common group that's added on via phase 2 is glucuronic acid or glucuronides. That's this sugar molecule right here. Ignore the phosphate I just circled, although that is also important. I'll get to that in a second. So this is actually what glucuronide is. And glucuronide is unique in the way that it's transferred. It's really hard to tack like a sugar, like glucuronide, onto something. It takes a lot of energy. So we have these phosphodiester bonds. In the donor for glucuronide, essentially uses the energy from these bonds to tack a glucuronide onto the molecule. And this substance is UDP-GA. GA standing for glutathione, UDP standing for uracil diphosphate. This sugar bone is a uracil, by the way, which, if you remember, is in RNA, but not DNA. But that's not super important. What is important, though, is just that glucuronide is not its own donor. It's UDP-GA. There are, as far as the most common other carriers we'll need to touch on are the sulfate groups, glutathione, as well as acetylation. I should have led with that. These are the four we're going to be looking at out of this list, but glucuronide is the most common. So what we also have is glucuronide in the transferase in the lumen of the endoplasmic reticulum. So if you remember back from MMP, what the endoplasmic reticulum does is it kind of will process proteins and molecules. Kind of makes sense to have our most common phase 2 enzyme here. In the fact that we will always be in an area where we're accessing these new products and can modify them. So that's something pretty important, is just that that's where glucuronide transferase is. Sulfur transferases, on the other hand, are in the Golgi apparatus. These are another very common kind of phase 2 enzyme. They'll add on like a sulfonyl group or sometimes sulfoxides. It kind of varies. But the primary form of sulfur transferase that will work on external drugs is sulfur transferase 1. So I would know this just in case. And there is a cofactor for sulfur transferase 1 as well. It's not the sulfur donor itself. Or actually, no, I'm sorry, it is the sulfur carrier. What am I saying? It's this molecule right here. It's PAPS. I'll write it a little bit bigger so you can see it. And this will just essentially use the energy from this phosphate bond to donate this sulfoxide, or sulfhydryl sometimes, but usually it's the sulfoxide actually. So yeah, using that PAPS molecule and I guess it's just a phosphate bond. It's not phosphodiester because there's only one. We can donate those sulfurs and tack them onto a molecule. Okay, next up we have glutathione, which is another one of our phase 2 conjugates. This one's special in that glutathione acts as a nucleophile as opposed to an electrophile. When I say it acts as a nucleophile, I mean glutathione is the nucleophile and there is an electrophilic drug. And why is this, right? When we tack on a glutathione, essentially the thing that attacks the molecule is this sulfur group. You can see it here attacking this epoxide at one of the carbons to make it tetrahedral, which that's not super important, but just know that carbon, since it has that oxygen on it, the oxygen is pulling away that carbon's electrons. Sulfur has a lot of electrons to give, so that's why this will act as a nucleophile. A nucleophile is something that has a lot of electrons that wants to merge with something without a lot of electrons. Whereas our other drugs, glucuronide and sulfur, the points of attachment were electrophilic on those two molecules, meaning we wanted nucleophilic drugs. So that's just kind of an interesting fact. That will probably be a question because that was stressed a lot. That's kind of what makes this special. Like I mentioned before, glutathione can actually detoxify acetaminophen if it's in that NAPQI form. The last kind of molecule I wanted to talk about were N-acetyltransferases. This one is special, and this will actually make molecules more lipophilic. And when we add on the acetyl group, what we're actually adding on is this CoA group. So that's, yeah, this right here. And it will use this class of acetyl coenzyme A. But the rest of this molecule doesn't come along with it. The part I just circled, It's only the really small part that gets added onto molecules. And since it's such a small molecule with a carbon chain, it will actually make the product more lipophilic. So a little bit worse for absorption, or I mean not absorption, I'm sorry, elimination and clearance, but it at the end of the day will do what it needs to do to get drugs out of the body. If it's so bad that it's sticking around, another enzyme will eventually come along and add something that is hydrophilic to it. All right, so now let's get into some of the math behind transdermal delivery. One of the things I want to stress, and I'll probably even say this later in this video as well, just because I feel like it's always in my notes for these slides because it's so important. This will be a question, don't get it wrong. It's that transdermal delivery is systemic and topical is only local. That's the difference between these two. I would be shocked if that was not a question. With that out of the way, let's talk about just some of the properties of this. So we have this property called flux. What is flux? It's essentially how much of something will move based on given preconditions, because it's not a rate, right? Rate is flux times area. And you can see here we can actually rearrange this equation to get this equation. You can see that area is also in the denominator of this, but it's not really a dependent of flux, because here you can see that flux is also independent of area, at least when it comes to rate. So it's really weird. I just like thinking of flux is if there's, because it's based on two things, right? You have your number of like molecules and the area you can get them across. Flux is almost like the potential of how something can move. And area kind of isn't a factor. If there's more area, things can definitely move across it more readily, but flux is not rates, and that's where it's a little abstract, but I'm hoping this example will clear it up a little bit. So for this first problem, it's asking two things. Which has the highest transport rate, and which has the highest flux? I want to start with flux. Flux is simply based on, if we ignore area, the amount of substance that can be moved in a given time. So for this, we have 4 particles of drugs, and for this, we have, I don't know, like 7. So let's say we just give this infinite time, right? Or let's say it'll move at, they'll just all move in an hour. Let's just say all these little drug particles. And let's say an hour has passed. We've moved 7 in this time. We've moved 4 in this time. And even though they had the same amount of time, if there was the same concentration of drug, yeah, I mean, they would have probably moved equally, but they didn't, because there was more concentration of drug on the right. So when we're just doing flux, B and D are actually equal, because there was simply more stuff there to move. Flux is just based on amount of stuff. Try and remember it like that. Now for rate, it also takes area into a factor. So if we have a higher flux as well as a higher area, rate will be higher. So what does that mean for the purposes of this problem? What it means is, even though these two were equal in flux, this one's bigger. This one has more area. So B will have the highest rate and an equally high flux to D. Because there's an equal amount of stuff, there's just more space to deliver the stuff in B. So going back to the example of an hour, if all these substances can move across the small one in an hour, the big one might be able to move all the substance in like half an hour. It really varies and depends, but that's the difference between flux and transport rate. So I hope that makes sense. Some other equations and numbers to talk about is P. P is a permeability coefficient. It can be similar to log P. It can be equivalent to log P in a lot of cases. Things we learned back in fundamentals, Kp and log P. It might not be also, because there's some other factors that go into it. I don't remember, because I record these slides out of order, if we already talked about the epidermis having a different permeability, specifically the stratum corneum, than the rest of the epidermis and the dermis. This can kind of be where that comes into play. But there's no point to getting into that for this class. That's just too much detail. So yeah, it's just think of it as Kp or log P. something I want to mention is since the skin is meant to be a barrier layer, its permeability coefficient will usually be kind of in the ballpark of 10 to the minus 7 or like 10 to the minus 9. Um, Whereas something like the stomach mucosa, right, still protective, way lower. Because once you're in the GI tract, we want to absorb. We're talking like to -4, -6. So you can see that these above are like the stomach is 1,000 times more permeable than the skin, which makes sense. And because we want things absorbing in the stomach, we don't really want things absorbing in the skin. Um, a few more concepts I want to point out. The HM is essentially the thickness of a membrane, which makes sense since this is an inverse relationship, because this is a proportionality symbol, in case that wasn't clear. The thicker a membrane is, right, the harder for things to pass through. The denominator gets bigger, lower the value is, so it's an inverse relationship. This is also the same with the radius of the drug. We assume the drug is a sphere, just for simplicity. The bigger the drug, right, the higher the radius, the less it's going to absorb. Just because, you know, a big thing is going to move through a membrane more slowly. It's going to get caught, especially if it's like hydrophilic. There aren't going to be as many pores that will fit it, that it can move through. Just won't move as much. And this last one's just a math equation. This is the equilibrium constant. We talked about it a bit when it comes to rates. This is permeability, right? Same as in this equation. And this is HM. I just couldn't annotate the little m part of it. Yeah. Okay, so now that we've talked about just kind of the basic properties of flux, let's get into the math, because this is what you're all here for. So if we're given a table like this, right, we've got amount delivered, patch area, time, drug concentration. For this first part, we want to see two things. We want to see most effective delivery, and we want to see most permeability. So what are we looking for? Whenever we say effective delivery, we're talking about flux. This first one, we are just comparing the fluxes. We're seeing what's higher. Permeability, we're comparing P. So what you can probably see what we're doing is in the first part, we're finding flux, and then we're using this equation right here to divide flux by the concentration of drug, and that'll get us permeability, and that's how we rank them. So with that, let's just get into it. Here is our flux equation, and we'll start with this row. We have change in drug, which is essentially equivalent to amount delivered in a certain time, right? Because it's change in drug over change in time. We have 10 micrograms in 1 hour. So if we have our Q, delta Q times area divided by delta T. For this first one, we have 10 divided by area is 20 centimeters divided by T, which is 1 hour. So we get 0.5 microgram centimeters squared hours. Those units will be the same for all of these, so I'm not going to write that again, but that's there for you. So this first one's 0.5. Let's move on to the next one. So 10 micrograms divided by 40 centimeters area times 0.5 hours. So we have 10 divided by 40 divided by 0.5. We also get 0.5 microgram centimeters per hour. So these two, 1 and 2 are actually equivalent. Let's see if 3 is equivalent as well. We have 15 divided by 20 times 1 hour. So 15 divided by 20, and then 1 hour. We actually get 0.75. So you can see for this one, the most effective flux is number 3. So 3 is the most effective delivery method. But now let's move on to permeability. So now that we've had these fluxes, right, this is flux 1, 2 was this one, 3 was this one. Same kind of thing. If we know that flux equals permeability times concentration, we can extrapolate that permeability equals flux divided by concentration. So let's do that. So we'll do formula 1 first. We have 0.5 divided by the concentration, which is 50 milligrams per milliliter. And here's where it gets kind of weird, since this is only asking for the most permeability. I guess we don't need to do this for this problem technically, but we should. We should convert milligrams per milliliter into micrograms per milliliter. 1,000 micrograms in a milligram. So this is really 50,000 micrograms in the denominator here. So 0.5 divided by 50,000, we get, I believe this is 1 to the negative fifth. It's a 1 like following 4 zeros. We'll do 1e negative 5. Since the flux is the same for system 2, I'm just going to leave that 0.5 there. However, the concentration for formula 2 is 25. So we'll have 25 milligrams per milliliter. To make that micrograms per milliliter, we'll add on those 3 zeros. So 0.5 divided by 25,000. We get a 2 preceded by 4 zeros. So this is 2e negative 5. And then finally, we have formula 3, which is 0.75 divided by 75,000. So when we do that, we get 1 times 10 to the negative 5. So for this one, we can see that in terms of permeability coefficients, 1 and 3 were actually equal. However, formulation 2 actually has a greater permeability. And this can be just, there's maybe some kind of chemical agent in the patch that's making it so 2 can deliver a little bit better. But yeah, so as you can see, flux doesn't always mean a higher permeability, and higher permeability doesn't always mean a higher flux. That's an important thing to remember. Just do the math. If you can get confident with this, this shouldn't take you too long. But yeah, let's move on to this next one. So for this one, it's a little bit, I wouldn't say harder, it's just a little bit more abstract, I think. How much drug can be delivered in an hour? So if you remember, our rate of transport, or rate of drug delivery, is our flux times our area. We have our area, and flux is ever so conveniently marked with a question mark in this table, meaning that we probably have to solve for it. But the problem here is we don't have like our delta Q, we don't have a delta T, so how do we get our flux? If you remember our other equation, our one we just used, is we can also calculate our flux from our permeability and our concentration, which we do have our permeability and we do have our concentration, so that's perfect. So all we have to do is we have our 5 times 10 to the negative 8th, that's our permeability, multiplied by 10 milligrams per milliliter. This is over second. This is centimeters per second. And something interesting happens here that I want to show off. The units actually are important. You might be wondering, since flux usually has an area in the denominator, how do we get an area with these units, right? We have a centimeter, we have a milliliter. 1 milliliter is equivalent to 1 cubic centimeter. So what we can do actually is, instead of writing that equation as a milliliter, we can write it as a centimeter cubed. What this does is these units will actually cancel somewhat. This centimeter in the numerator will cancel with one of these centimeters in the denominator and leave us with centimeters squared instead. And that's how we get flux. So now it's just a matter of multiplying. So 5 times 10 to the negative 8 multiplied by 10 milligrams. We get a very low number of 1, 2, 3, 4, 5, 6, 7. It's 5 times 10 to the negative 7th milligrams cm squared per hour. We could make this microgram if we wanted. If we convert this to microgram, we can make this number a little more reasonable. Oh, I'm sorry, this isn't per hour, this is per second, and that's why it's so low, because second was in this equation. So per second And I'm going to convert this to micrograms to make this number a little bit better. Since a microgram, there are 1,000 micrograms in a milligram, this would actually only be 5 times 10 to the negative 4 micrograms. And we can leave that in seconds for now. That's fine. Oh, actually, no, we can't, because haha, I made the problem an hour. Okay, so that's not too bad. So now we multiply this 5 times 10 to the negative 4 times 3,600, because there are 3,600 seconds in an hour. And then we get a more reasonable number. We get that we have 1.8 microgram per cm squared times hour. But that's still not our rate, right? This would be our flux in an hour with all these unit conversions. But we also need to consider our patch area. Because remember, flux times area is what actually gives our final. So our final answer is we just multiply by 10 centimeters. It's getting really short in space. But we'd have 18 micrograms per hour. Because these centimeters squared here will cancel. I couldn't really write that one on the right, but since the patch area is 10 squared centimeters, that's how we got that. So you can have 18 milligrams per hour. That's pretty decent. This next one, a couple ways to solve it. So there's two methods, really. And I kind of wrote this not how I wanted to. I wanted to ask how long it would be before this patch is unviable. I asked how much drug would be delivered before the patch is unviable. I'm going to show you how to do both, because I think both are really valid questions which should show up. They'd probably be one of the harder questions on the test, so knowing how to do them would be really good. So since I asked how much drug can be delivered first, let's start with that. So this is just a fact we need to know. A patch becomes unviable when there is only 90% of the patch left, right? Or is it 95? We'll do both. I mean, the method is the same. I'll need to double check that. Maybe it was 95. Okay, well, shoot. Regardless of it's 90 or 95, I'll make a note of that probably in the next math example I do, because to be honest, I've already recorded the other parts of this video. I did the math last. So I will go back through the notes and I will update that. But for now, we'll just do 90 because it doesn't really matter that much. So to find out how much drug will be delivered before there's 90% left, how do we do that? So first we need to find the amount of drug in the patch, and we can actually get that from this table. Really easily, actually. We need to find, so one thing we kind of know about how much drug is in the patch, we know there's 10 milligrams per milliliters, but how many milliliters is a patch, right? How does that even work? So what we can do is we can start with our 10 milligrams per milliliter, but what we're going to do is do the conversion we did in the problem above, which is really helpful. We have 1 milliliter equals a centimeter cubed. So now all of a sudden we have 10 milligrams per centimeter cubed. How many centimeters cubed do we have? Well, we have an area of a patch and we have a thickness of a patch. A thickness is basically just the height. So what we can do is we do area times height. That gives us a volume of a rectangular prism. We can do 10 centimeters squared times 0.1 centimeter. And this will be equivalent to 1 centimeter cubed, right? Because the centimeters units will multiply together and kind of add. So if we have centimeters cubed in the numerator up here and in the denominator, they just cancel. And we get that there's 10 milligrams total in the patch. So now what's 90% of 10? It's just 9. So once this patch only has 9 milligrams left, assuming it is 9 and not 95%, the patch would be unviable. And if it is 95%, then it would be 9.5 milligrams. So that was the problem I did put on here, which I think is a little bit easier and a little bit less abstract. Let's do the harder method now. So how much time until the patch is unviable? How do we do that? So this is 90% for sure. A patch will, or yeah, I just confirmed my own theory. So it is 90. It's 90% when the patch runs out. Because we set this problem up like that. Duh. Okay. 90%. I'm just dumb. I'm tripping myself up on things that I know. Don't worry about 95. It's 90. Anyways, how do we do this? We can use this equation. If you remember, we've used K before for half-lives, right? When 50% of the drug is gone. We're going to use it for like a 9/10 live right now. When there's 90% left. So to find K, we need two things. We need the permeability times the thickness of our patch, which you might think is kind of arbitrary, right? It's the way I like to think about it is, let's say like gravity is the thing that's driving this permeability factor. The patch will start out completely full, but as gravity pushes things through, over time these levels will get lower, right? So this blue is a little bit lower than this red, where the red peaks are. Then it might go to green, right? The patch is essentially draining over time. And what we do through this is we essentially find out um, when the drug will have completely drained from the patch, kind of. Except we don't care when it's completely drained. We care when 10% of it is drained, because that'll bring us to that 90%. So really that line is kind of up here where the red was in the first place. It wouldn't be down here with the purple, because at that point it would be like when 80% of the drug has probably left this patch. But that's just the theory. That doesn't really matter. It's really just the math that matters, and the fact we can do this on an exam. So I'll show you how to do that. So if the equilibrium constant is just P divided by H, we have our permeability, which is 5 times 10 to the negative 8th, divided by our thickness, which is 0.1 centimeters. This is also centimeters per second. And just so you can see how this cancels, we have 5 times 10 to the negative 7th. And then this is over seconds, right? And if you remember, K is always, its units are 1 over seconds. So this makes sense. That's how we know we're on the right track with that. So now, all that's left is our 9/10 life. If you remember, the way we get half-lives is we do the natural log of 0.5, right? The reason, and that gets us 0.693. The reason we do that is because we're looking for half, right? It's a little bit different if we're looking for 90%. If we do the natural log of 0.9, so ln 0.9, right, when 90% of something is left, because 90 is equivalent to 0.9, 90% is, I should say, we get 0.105. So this is our constant for this. This is like what our 0.693 is, except this is our 90% constant. Then if you remember, the equation for, like, we'll just call it 90% life is equal to ln 0.9 divided by K. So we'll use that K we just calculated, that 5 times 10 to the negative 7th. I don't know why I erased that. That's like the one thing I needed to keep. Good thing I memorized it. And from here, we will simply get 0.105 divided by 5 times 10 negative 7th. And that is, we get 210,000. That's in seconds because our unit here is in seconds. So I'm just going to divide that by 3,600, right? 3,600 seconds in an hour. We get 58 hours. So this would approximately be like 2.5 days that this patch will last a person before it runs out. And that time it will run out is the time it will run out is the 58 hours, but the amount it will run out by is 1 milligram. So kind of a way we can check this is if we know that the permeability, essentially just reverse engineering it, right? So we could find out based on the permeability how fast it's moving. So like we'll remultiply this to 210,000. 210,000 times 5 times 10 to the negative 8th. That's our permeability coefficient. we get a value when we do that of 0.105, which is approximately 1/10 of this value, the thickness. I know I didn't just write that down, and honestly, it's not super important. That's just a way to double check yourself. But if that helps you, essentially, it's like how much has moved in 58 hours, and you get 0.01 centimeters. 0.01. It would help if I actually wrote it correctly too when I'm doing all this extra math. Don't worry about that last part. It's just how I check myself and how I think about it. Okay, so now let's talk about transdermal and topical delivery. Before we get into that, I wanted to start talking about the skin a little bit, or the epidermis and the dermis. So, what is the layers of the epidermis? You start with your stratum corneum. These are all dead skin cells. And then your epidermis has these layers which are alive. The stratum basal is the lowest layer. You have the dermis, the papillary layer. This is actually what makes up our fingerprints. It's kind of a fun fact. It's not super important. And the reticular layer, and under that is subcutaneous tissue. Something unique about the epidermis is that it does not have vasculature. So the reason layers like the stratum corneum are dead is just because they don't get blood flow. And as you get further in, further outward, further superficial with your layers, they will start to die just because they're away from blood flow. The stratum basal has vasculature the closest, so that's where the epidermis will multiply. Um, but yeah, basically just outwards is more dead. There's various proteins in the epidermis. You can see they also have different expressions. So you have these like these laminar granules, for example, a little bit deeper into the skin, this being the superficial side, the most outward side. But primarily, once it gets to like the stratum corneum, we have keratin, which is the primary protein. And really all keratin does is it's a very rigid protein. It's also what our hair and nails are made out of. And that's just because we need our outer layer of skin to be kind of tough, right? We don't want it to just be able to be pulled apart easily. Keratin bonds will kind of allow things to be able to like stretch and not rip. And the other proteins have different functions, but they're not as important. The dermis, on the other hand, it does have blood. It has immunologic cells, lymphatic cells, as well as nerve cells. This is also where our hair follicles and sweat glands are. We have two types of sweat glands. I don't think that's super important for this class. Eccrine sweat glands are usually more, the way I think of it is more like sebaceous are some of our like more pungent sweat glands. So things in like our armpits, areas that sweat a lot more will generally be sebaceous, where eccrine usually have thinner solutions. Eccrine sweat glands also actually produce milk. That's kind of a fun fact. Um, and hair follicles will actually um, be, what's the word I'm looking for? I'm just going to say hooked up to sweat glands essentially to keep hair lubricated. Um, And something else is hair follicles will also contain stem cells. Kind of interesting. That's it's one of the few places in the body that have them. Obviously, like the bone marrow does. So just kind of a neat fact about that. Um, Hair is made of keratin, like I mentioned. There's a tubule that is kind of formed that the hair can reach out of. That's why you might get irritation if you have like an ingrown hair. That essentially means there's not a clear way to for the hair to come up. So it's kind of just like expanding in the area around it. It's causing a little bit of inflammation. Um, Something important to note is that with a lot of these structures, these sweat glands, these hair glands, is you don't get more from birth. Activity can change between now and birth. For example, you're not going to have a beard when you're a child. Um, or it's like you're probably not going to go bald as a child either, generally. Um, so it's really just the expression of different things in the body that will up and down regulate those. Um, Something else interesting is that birth, these are actually pretty uniform throughout the body. All these proteins, all these glands, all these follicles. Um, but when we get older, it seems like they're spread out in more places. Like I mentioned before with the beard analogy, it's like a beard is a very thick amount of hair versus somewhere like on a leg, you might not see as thick of hair. And why is that? The simple reason is the head will grow less than the rest of the body proportionally. when the body grows, these will all kind of be stretched out. They'll be spread out. And since your head's already really big when you're a baby and it doesn't grow as much throughout life, I mean, it grows, granted, but like compared to how much bigger your leg is as an adult to your head is just disproportionate. And that's why these can get spread out, some areas more than others. The head doesn't really grow, but a lot of the limbs will grow. And that's why hair is a little more spread out on the limbs. So how is skin actually modeled? It's not perfectly layered. The most recent accepted model, because this kind of changes and varies, is what's called the brick and mortar model. The brick being kind of layers of skin, which are these zigzag lines. In the mortar, more being the proteins and fats in between these cells. There's a lot of lipids, there's a lot of cholesterol between cells. You can see those here, kind of filling in the gaps. And you can see it's not like a perfect stacked kind of system. There's some things in more areas than others, um, that all kind of binds it together. Um, so now that we've talked about just kind of the basics of the skin, how are drugs delivered through the skin? Um, and there's two types of delivery. There's transdermal and topical. I will write this down because this will be a question. Transdermal, topical. The main difference is that transdermal has systemic delivery. These drugs will get into the bloodstream and move around the body. Topical has local delivery. It'll only affect things in the area. And there's two ways it can do this. Similar to how we've been observing drugs move through the body, they can move transcellularly, or we've been using the term paracellular up until now. Uh, Now we're using intracellular as our term. Um, and that just means they move in between the spaces of cells. They kind of move in the mortar area of the brick and mortar, where transcellular will just go through the bricks because that's what it does. Same thing as para and transcellular. Lipophilic drugs will move through like transcellular, right? Because they can just pass through those membranes. Hydrophilic drugs cannot because they'll be repulsed by lipophilic substances like a cell membrane. So they'll just kind of move in between. And because of this, lipophilic drugs are usually absorbed a little bit faster, just because they don't need to take the long scenic route. Um, as far as proteins and like lipids and things in the skin, I don't think we need to know that many. Something I would note though is that their frequency changes based on where you are. For example, polar lipids, they occur a lot in the stratum basal, right? Which, if you recall, was the deepest layer of the epidermis, versus the stratum corneum, they're hardly there anymore. They've been resorbed or they've been destroyed or one thing or another. By the time they reach the stratum corneum, there's not a lot. Something like sphingolipids, on the other hand, they occur a lot less in the stratum basal. By the time they reach the stratum corneum, they'll be much more frequent. Um, which is just maybe the cells in like the stratum um, granulosum produce them or something. I don't really know, to be honest. But just being able to recognize that even the lipids and proteins uh, in the layers of cells, in between the layers of cells, isn't constant. So that's just something to be aware of. Um, and I think that's everything I had to say on this slide. So now let's talk about some of the pros and cons of transdermal delivery. I'll try and hit on the big ones. Um, this isn't really a pro, it's included with the pros. I mean, because depending on how much it absorbs, right, this can kind of be a net neutral. Food effects is fine, GI tract metabolism. This is actually a pretty big one. I would note this one. Just for the fact that if, let's say like, I mean, it'd be really hard to get a protein-based drug across the skin, but let's pretend for a second we found a way. Obviously, proteins are totally broken down by the stomach, which is why we give things like insulin, heparin, IV, or sub-Q, right? So if we could find a way to make this like transdermal, that could be really positive. Same with first pass, very similar thing. Um, Patient compliance, convenient dosing is subjective, right? Maybe compared to like an IV or sub-Q, but like oral is objectively or subjectively just as easy. I'd say the biggest thing though is controlled release, and this is something we can do really well with these substances. And this is essentially the idea that, especially for drugs with a more narrow therapeutic window that we can work with, therapeutic index we can work with, in oral, right, it may have a peak in our body that we can't really control. Or same with IV. I mean, IV we could give a lower dose, but maybe that effect becomes subtherapeutic. Since transdermal products will generally have zero order elimination, meaning we can have, as well as zero order administration, meaning we're delivering and removing at a constant rate, we can actually come up with design systems to administer these to an area in really good concentrations. I would say this is the biggest pro of transdermal. It's just these controlled constant releases. And we'll get to some of the drugs these can be effective with in a little bit as well. And I can extrapolate a little bit more on why this is so essential. Cons is it's hard to get a drug across the skin. This is really big. Like if it's less than, or if it's more than 800 Daltons, it becomes a lot harder. If it's hydrophilic, meaning it would have like a negative octanol coefficient, it would be really bad. Uh, High local drug concentrations sometimes, but not really, because like I said, we can kind of control that with this. Um, Local first pass is pretty minimal. Patch can fall off, pretty minimal. That's patient dependent. Expensive is probably one of the biggest cons, just because it is not easy to formulate one of these. They only work for very certain drugs. They only work for very certain binders. Uh, so not great. But now let's talk about how we can kind of test some of these products, right? Because I've talked so much about controlled release and why that's important, but not so much how we would even begin to test that, right? Because you can give something to a patient, but how do we measure this? How do we know how much drug they're actually getting? For this, we have models. So these are called diffusion cells, these two things. This one right here is side-by-side diffusion cell, and this one right here is a Franz diffusion cell. Probably won't be asked this, but just for your reference, Franz is vertical, you're moving something through the skin. Side by side is, this is the skin right here, by the way. This is the skin right here, if that wasn't clear, is horizontal. So horizontal, vertical. I'll draw those arrows to make that more clear. Where do we get skin, right? Because we can't exactly get human skin very easily, which I personally think is a good thing. But and so generally we'll use animals. You can technically get human skin. Dr. Lee mentioned it. And the way companies will do it legally is you're not allowed to buy it off the company, but they'll include a really big service fee. So you're essentially buying a human organ, which again is like there should probably be some more clear regulations on that. So usually when we do use an animal, we'll use pig. Pig is like generally a really good one-to-one model with human for one reason or another. Not just for skin, but for organs as well. I don't know. In my high school biology, the animal we had to dissect was pigs, just because they were the most similar to humans. I know some people did cats. I know some people did frogs. It varies depending on where you go. But yeah, so pigs are really good testing models. Something else is even regions of the skin have variability, not just the species. For example, if you think about like the palms of your hands and the soles of your feet, um, they're very thick, at least comparatively to something like your face. So something thin, like your face, or genitalia, for example, will have a higher permeability. They're thinner, they're more sensitive, more drug can be absorbed. Uh, versus like a foot or the palm of your hand, you have this thick skin. It might be calloused, just depending on what you do um, throughout your life. And that can be harder for drugs to absorb through. Although they do have high water permeability, which is interesting. Um, I don't know if that indicates that if you had like a solution of a drug, if that would pass through easier, because I still feel like it might get caught up, especially if it is in a solution, right? It would probably be a drug that absorbs paracellular, or between the cells. So I don't know how well that would work, but if you could find a formulation, you could probably use that to your advantage somehow. It really just depends. Um, yeah. And then one last thing I wanted to talk about is this diagram. In PK studies, the stratum corneum is actually modeled as its own section, and then the rest of the epidermis and dermis are modeled together. And I kind of wanted to talk about why that is, at least in terms of PK studies, in case we see a chart like this, which we could. Um, if you remember, this stratum corneum is that brick and mortar model. So you'll have pores. These are essentially your like paracellular spaces, and you'll have lipids. These are essentially your cells. So this constant right here, this permeability constant, will kind of be based on these two factors, the permeability of the pore, which will be more useful for hydrophilic drugs that can't pass through the cells, and permeability of lipids for drugs that can pass through the cell that are lipophobic or lipophilic, I'm sorry. And this is more of an average. It's kind of like the ratio of pores to cells, and there can be other factors too. That's not important for this class, though. That's more important for scientific modeling. And then from there, right, we don't really have that brick and mortar model as much. I mean, we'll have some, but once it's kind of past the stratum corneum, this outer, tougher layer, we just kind of consider the dermis and epidermis to be the same thing, or the rest of the epidermis. So this is one constant. Okay, so now let's talk about this graph, because this is kind of important. This will be on our exam. This essentially is looking at two things with these lines. We'll talk about the x and y axis first. The x-axis, this is the first thing we're looking at in terms of how drug absorption is affected. It is the log K value, or your Kp. Essentially just how soluble you are in lipids versus how soluble you are in water. So you can see here the scale goes negative. A value that is less than 0 to 0, sorry, will be hydrophilic. And a value that is greater than 0 is lipophilic. Drugs usually like to be lipophilic if we want them to absorb well. Which you can kind of tell just by looking at this already. We have a much higher concentration of drugs at a higher log P or Kp, or yeah, whichever one you want to call it. It doesn't really matter. And then we mentioned this. This is the concentration. I'm just kidding. This is the log P. I meant log K. It doesn't change what I just said. Log K. Still solubility. This is just the concentration. Or no, this is permeability, which, yeah, okay. I'm getting ahead of myself. So permeability, if you remember, is directly proportional to flux, which is directly proportional to rate of administration, which is directly proportional to tissue concentration. Okay, there we go. So I took a few leaps there to get there. So log K is just solubility. We don't need to take any leaps there. A higher log P, a higher permeability, or log of permeability, will equal a higher tissue concentration, which makes sense, right? If something's more permeable, it's going to be in the tissues more. Okay, now that we're done with that, we can actually talk about the important things in the graph. And so what are we looking at? So this higher log octal constant, right? We know that lipophilic drugs like to absorb more. These lines here, I don't know how well you can see this. These lines each represent kind of a grouping of molecular weight. You can see a molecular weight of 300 to 600 is like this line right here, roughly. And then higher molecular weight, or lower molecular weight, this is 50 to 200. I'll just write these to make it easier for you to see. 300, 600, boom. Okay, this is higher up. And we kind of talked about this back when we talked about flux. Something with a bigger radius has less flux. So it makes sense that something with a smaller radius, a smaller drug, would have a higher flux, which, you know, going through all these, would have a higher tissue concentration. So that's essentially what this is showing. And then beyond this, there are two additional lines that I think are really important to notice. We have this line down here, this PP line, as well as this line up here, this PDE line. PP stands for polar porous pathway. I don't know if that's how you spell porous. I want to say it's OUS. Not important. What is important is this is the primary transport mechanism of hydrophilic drugs. Now, why is this? We've alluded to this so far. Hydrophilic drugs can't really go through cells, right? They move that in that paracellular route, so they move where there are pores. Um, if you think back to that brick and mortar model, where they can kind of like squeeze around cells, they don't really go between cells. And those spaces around cells, we just think of them as pores essentially, that they can work their way through. And you can kind of see why is since we have these really low um, log Ks in this area, right? These really low, you know, the low log K means high hydrophilicity. It makes sense that this is the area. Alternatively, this PDE line is known as your dermis control, in which this is essentially it's when the drug will move transcellularly. Um, right, because lipophilic drugs can pass through the cell membrane. Um, and yeah, that essentially just allows them to, with a higher octanol coefficient, they can absorb more into the tissue. And if you remember why this line is so much higher as well, is because lipophilic drugs will absorb a lot faster and a lot more, right? Going back to our permeability, higher rate also means higher tissue concentration. Same kind of thing. So all this chart is telling us is that molecular weight is inversely proportional to concentration, and log K is directly proportional to tissue concentration. Okay, so now let's do one last kind of calculation problem for this video. Um, we want to find out if this drug right here, nitroglycerin, would make a good candidate for a transdermal product, assuming we want to deliver 10 to 20 milligrams a day. One factor we don't have, and whenever we're not given this, assume this is the kind of the standard. Patches are 20 centimeters squared. We're not given that in this problem. It's always a safe assumption. This is how big a patch should be. Ideally, maximally. You can increase it a little bit if you need to, but like just stick to 20. So first, I want to use this graph up here, show you how to use it we're given permeability, but I want to estimate it based on this chart. So how do we do that? The first thing we want to do is we will look at our molecular weight, right? We have 227. Now, we don't really have a molecular weight that falls in this value with these lines. We have 50 to 200, we have 300 to 600. Obviously, it's going to be a little bit closer to the 50 to 200. So we'll just do the line right below it, right? Because if you remember, higher molecular weight indicates lower permeability. So if we get 227, we'll just say it's that dotted line, right under 50 to 200. Next up, we want our octanol coefficient, or log K oct. One is right here. That's this vertical line. Essentially, what we're doing is we're just drawing a vertical line here, and then we'll follow this dotted line graph, and we'll make a point right here. This is what we can assume the permeability of our drug is going to be. And then this is really hard to see. This is 1 times 10 to the negative 3 centimeters per hour. Now, this isn't the value we're going to use for this problem because we actually are given the permeability of this 0.01 centimeters per hour. You can see it's off about 10 times. It's not a perfect system, but you know, it's better than nothing. Like, being an order of magnitude off is obviously not great, but it is better than nothing. So we'll just go with our 0.01 because that's already there. What do we need to do first? So first thing we need to do is we need to find the flux. If you remember, flux equals concentration times permeability, which we have. So our concentration, we want this to be 1.3 milligrams per milliliter. We are going to need to convert this to centimeters cubed later. I'm going to do it now. We did a similar thing in the previous example. So 1 milliliter is 1 centimeter cubed times 1.0 or 0.01, sorry, centimeters per hour.
So you can see here, centimeters cancels, leaving our flux to be, let me plug this in really quick, 1.3 times 0.01. I don't know why I put that in a calculator. I could have totally done that in my head. We get 0.013 milligrams centimeters squared, because of that cancellation we just did, per hour. This is our flux. So now we need to determine our rate of transport. If you remember, rate is equal to flux times area. Area we gave ourselves, it says 20 centimeters squared. So if we do 0.013 milligrams centimeter squared, that's a C, sorry, per hour, times 20 centimeters squared canceled, 0.013 times 20, we get 0.26 milligrams per hour. The dose we need to deliver is 10 to 20 milligrams per day, so we do have one more step. We need to do 0.26 milligrams per hour times 24 hours in a day, right, just to see if we can deliver that. When we type in that value, we get 6.24 milligrams. So this is less than our 10 to 20 value, right? This would mean this is not a viable drug candidate per se. It's kind of borderline. You could make a judgment call, right? Because if this is 6.24 over 10, our like minimum value, this is 62%, basically. If we were to design a patch that was 38% bigger, so that would be, let me do the math really quick. We need a patch that's realistically 31 square centimeters. This isn't super unreasonable, to be honest. Like, let's say with our 20 centimeters, we have a patch dimension that's like 4 times 5 centimeters. Maybe 6 times 5 centimeters. This is within reason, so you could argue this one. That's kind of why I picked this borderline example, just so you could kind of be aware of really close examples like this. Usually the example will not be this close. So in this case, you could kind of make a judgment call either way, being like, no, this patch needs to be small, especially if it's a patient that's like, I don't know, like on the move or something. There's a chance the patch falls off, or it would interfere with their day-to-day life. But if it's like something from more of a sedentary condition, or it's like a less active patient, we'll just say, you could definitely make the call just to increase that patch size a little bit. But yeah, that's pretty much how you do a problem like this.
Okay, so now that we've talked about some of the math behind transdermal systems, let's just talk about some of the factors, what drugs they're good for. So I alluded to this in a previous slide, when we can use these. So what are these good for? So they're good for things that we kind of need to treat all day, right? We don't want a patient feeling any pain at any point in the day, so pain management's really good. We don't want a patient's blood pressure to fluctuate a ton, so we've got this. Addiction, to both like smoking and I think opioid addiction is somewhere on here, um, are really big things, right? Like these can't be reduced throughout the day. The other disease state that or not disease state per se, but kinds of diseases we need to treat with these patches are for patient-related factors. When it comes to a drug like or drug classes. Sorry, I'm like searching through them. I know they're in here. Da, 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 da. So like ADHD, right? If a patient already has trouble focusing or remembering to do things, just depending on their day-to-day activities, they might not be able to remember to take an oral drug every day, unless they like have a pill box and are super good about it. It could be very distracting. Same with dementia, I know is on here. So patient-related factors due to diseases can also be a reason to use these drugs. And just to make sure adherence is good. So it's kind of like duration and adherence. I like that a lot, actually. I just came up with that. So two types of things. If it's something that needs a high duration or something that needs a high adherence, that's when a transdermal system is really good. Then different types of patches. This right here is called a reservoir patch. You can tell that because of this kind of lump inside. This white space, this reservoir, is all drug. And these were used for fentanyl patches for a while. They're not really used anymore because the drawback of these is you can kind of just extract the drug from this using like a needle or something. Uh, and that's obviously not very good if patients are able to get this fentanyl they're supposed to be receiving all day or maybe over multiple days and then have it and then inject it in one dose, especially because the fentanyl is used for addiction. What we use a little bit more now are these adhesive matrix patches or adhesive or matrix. They're technically different, but they're very similar. Um, for an adhesive patch, the drug will actually kind of be in the, I'm going to write the word glue. It's not what it is. Adhesives really is a better word, but I don't want to say the adhesive in the adhesive patch. The glue will contain the drug. Um, and it might also be formulated to benefit absorption. We'll talk a little bit about some things that can upregulate absorption of a drug or regulate absorption of a drug, because it can even be downregulated if the drug absorbs too quickly. That's pretty rare, but I mean, it can happen. Um, and then for matrix patches, it's very similar. The adhesive doesn't contain the drug, but the patch has some kind of film layer that can have the drug, or there's a lot of different ways those work. That's not super important though. Something else are like emulsions or gels. A drawback to like an emulsion or a gel is the fact that these can be like moved off the skin. So you might, let's say you're like, I don't know, you are touching somebody's arm, and they have a lotion that has a drug in it. You could get some of that drug effect. Or you're like holding a baby. I like this example better. You wouldn't want to like have the baby receive some of the drug you have from your lotion, right? Because it's slowly absorbing over time in the skin. And even if you've like have most of it washed off, you're still gonna have that kind of oily coating uh, on you. And then there's also things like sprays as well, which can also administer the drug. You can see here, this is like a spray bottle. It's kind of got this enclosed area. So this is when you spray, the drug won't just fly off randomly. It'll all be kind of located in this area so it can absorb. So that's a pretty smart design. Pretty similar drawback though to the gels, just the fact that if this is still on your body, right? And if you touch something you shouldn't, whether that be like maybe it just rubs off on like a surface, or if again if it gets absorbed by another person, that can be kind of unideal. So now that we've talked about some of the ways that you can apply like a transdermal or topical product, let's talk about some ways we can enhance their absorption, right? Because not all of these drugs are going to want to get into our skin very easily. So there's a couple ways we can do this. We have our physical enhancers and our chemical enhancers. As you can probably guess from the names, the physical enhancers will not be drug related, right, or chemical related in this case. Um, we have iontophoresis as well as high electric field electroporation. These both use electricity. We have sonophoresis that uses sound. And then we have different methods to like puncture the skin, punctuation. And then we also just have heat. Um, and then chemicals, um, sorry, chemical enhancers will work more by altering like a property of the drug or the skin to help absorption. So let's begin with iontophoresis. Um, Iontophoresis, similar to what the name would imply, uses ions. You have a system of what is called an anode and what is called a cathode. This drives me crazy because anions have a negative charge, but an anode has a positive charge. A cation would have a positive charge, but a cathode has a negative charge. And the reason for this is because essentially ions will move towards the cathode, anions will move towards the anode. Um, so what you usually do when you do iontophoresis is you'll exchange some kind of salt, right, NaCl, through one of the sides, either the cathode or the anode. I'm sure it matters, but I don't think it matters for this, and I didn't take the time to memorize it. Um, and then the drug through the other cathode anode. So let's say it's a positively charged drug like lidocaine. You could have like lidocaine chloride and you could essentially move that through the skin as it would attempt to move to the other side, uh, to the anode, or let's say it would start on the anode. This is like their final position. So it'd be moving this way. So it'd start at the anode, and you'd be moving it through to try and get it to the cathode. But then once enough had gotten like through the skin and it was moving, you could essentially stop the charge, the current, in order to, it's like, oh, well, I'm just stuck in the skin now. I guess I'll absorb into the body. Um, Same with dexamethasone. This would start at the cathodes because this has a negative charge. So you could do like sodium dexamethasone. Same thing, start to get it moving through the skin and then stop the current so then it's just kind of stuck in the skin and can do its thing. A drawback to this method is, well, I'll lead with this. A drawback to a lot of the methods that I'm about to talk about is they are not covered by insurance. First of all, they're all very expensive. A lot of them are experimental, and I personally doubt we'll see many of these on the market, at least in like large scale uses. Like you're never gonna have most of your oral drugs replaced with like iontophoresis. But there are a few niche use cases, which I will go over, which have been market approved. Um, but for this specifically, the biggest kind of reaction is you can get skin reactions if you do this for too long, right? Which kind of makes sense. You're putting electrical devices up to your skin. Kind of makes sense. Your skin might burn, might get redness on your skin, irritation. And this will usually occur at a chart or a current greater than 0.5 milliamps, which honestly isn't even a lot. Like I think if you ever were to look at like the amps on one of your devices, even like a household appliance, it would probably be, I want to say an outlet can output 120 amps. Maybe that's volts. Regardless, the point is this is a very small number, but you're still putting electricity on your skin. So these actually are probably the most used of a lot of these methods we're about to talk about. You have this patch right here. This is like a fentanyl patch. But the benefit of it is you can essentially press a button whenever you have a craving or whenever you have pain, and it will release a certain amount of fentanyl. Um, it also has a timer, so you just can't keep pressing the button, or I guess you technically could, it just wouldn't release the drug. Um, this is like a smoking cessation watch. Uh, I just think that's kind of funny. You've got that smoking cessation drip. But anyways, this will test certain chemicals kind of in your um, like cutaneous skin region. I think you can also do it manually if you have a craving, and it'll just release. I don't know if it releases nicotine or if it releases something else. Probably nicotine would be my guess. And then you can also do this for, I think this is like an acyclovir device. You can essentially just use this to administer acyclovir. It'll put a current into you and you will have the antiviral in that area. Um, Sonophoresis is another form of physical delivery. This will use sound waves to deliver drugs. And essentially, this is different from a like an ultrasound, right? Because both of these are using ultrasound to deliver drugs, but this is different from an like imaging ultrasound in two ways. The frequency of the sound waves will be lower, so lower frequency, and you can also think of that as like lower pitch. The sound waves aren't spread out as much, and they will have a higher amplitude. This essentially means they're louder. Uh, so if you were to run one of these, you'd probably hear a really loud amplitude. Wow, I can't spell. That'd be a T. It'd be really loud and really low if you were to run one of these to deliver a drug. And these like aren't on the market really. They were, but they got taken off the market for like, I think this was like these two things were diabetic therapy to deliver like glucose maybe in hypoglycemia. Uh, but the product failed because if you had hypoglycemia, you could just also eat a snack. So a lot of these aren't super practical, but yeah, they exist. So just be aware of them. So now let's talk about electroporation. Iontophoresis, as you recall in the previous slide, also uses electricity. I would compare iontophoresis to be more of like powering something with an outlet, right? Like you have this consistent current that's passing through it. Um, low energy, slow. Um, Electroporation is kind of the opposite. It is very short, so like you can see here, like it can be less than a millisecond and 1000 volts. So this is like administering a drug with a lightning strike. You are inserting so much electricity, electroporation, you are burning a hole through the skin to administer a drug. Uh, so as I'm sure you could probably imagine, one of the side effects of this is pain and burns. Granted, it's very short, but yeah, and again, this isn't very popular with people. Um, One other big side effect is this is so much more electricity in an instant than iontophoresis that you might get like a spasm. Uh, so you actually have to pinch your skin up just so you don't hit a muscle, so you don't like jerk your arm or wherever you're administering and like knock over the device or hit something or hit your hand or arm on something. Yeah, so as you can tell, I'm a little bit biased against this route of delivery. Uh, but it is something that exists. This next one is probably one of the more practical forms of delivery. This can actually be used in a lot of cases and probably has some more applications that can be explored. They're microneedles. Essentially, the way I think of these is like a little bed of nails, which does sound mildly horrific, but they are so small you don't feel them. Each one's like the diameter of like a mosquito's, would that be like a proboscis? I have no idea what their nose is called. Um, it's like poking you, but it's so small you don't feel it, right? There's a few ways these microneedles can administer a drug. There's four ways. This might be a question, honestly, so it's worth noting. The first method is these are just solid needles. They'll poke a bunch of holes in your skin. You'll have like this area with a bunch of craters now. Granted, we can't see it with our naked eye, but they are there. And then you kind of just apply the drug, like a patch with the drug, and those holes will be filled with the drugs, the holes that the needles left. The next thing is they'll still be solid needles, but you can see here they're drawn in blue. When they come out, they're white. These are like there's a film coating of the drug on the needles that'll stick around after you pull the needles out, and then that'll diffuse. So the needles are still intact. It's just the film or the solution that was on them is what stays in the skin. The next one is these are needles that are made of like a polymer or just some other solid substance, but it's got the drug in them. And then it won't melt at room temperature, but it will actually melt at skin temperature. So these needles, which will have the drug inside of them, will melt in our skin, and then the drug can diffuse. Um, and then the last type are these needles. These are actually hollow. So what you do is you stick them in and you apply the drug to like the top of this bed while it's still in. You're essentially like giving a bunch of little vaccines then, because these will all shoot drug into the skin through those holes, and then that'll diffuse. So again, these are a lot more practical, right? Because you don't really feel it. There honestly aren't really adverse effects to this one. They're a little bit expensive and experimental still, but as far as the physical barriers or physical methods we learn in this class, I think this is honestly probably the most practical. Um, so there's something to be said for that. Um, Laser delivery is similar to a microneedle in the fact that it's creating a hole in your skin. However, you're burning a hole in your skin. So this is kind of similar to electroporation, to be honest. And since like a laser that's strong and that precise, not to like, burn through us, is hard to produce. These are more expensive. Um, yeah, so it's not as practical as something like a microneedle. Some of the last methods are you can also do microporation, making the hole right with heat. Similar to the laser, you are essentially burning a hole in yourself and putting drugs in that hole. Um, Again, not very pleasant, kind of expensive, and not really worth it. This next method is a little more worth it. You're using low energy heat. Um, and there's an equation right here, which I'm not quite sure why Dr. Lee included it, because I think it kind of takes away what he's trying to get across with this. It's this diffusion, right? Diffusion's equal to equilibrium times temperature divided by 6 pi. I don't know what R in this, the this is viscosity of the matrix, and R is maybe like radius, so it's maybe like a length value. but essentially it has T in the denominator here, right? Which would lead you to believe that diffusion increases with heat, which it does. But you have to keep in mind, this is low energy heat, right? If the surface of our skin is like roughly, I want to say it's like 80 degrees Fahrenheit, this isn't meant to burn you. Anything will start to feel like burning really above like 100 or 110 degrees Fahrenheit. So these are probably around 100 or 110 degrees Fahrenheit. That's something like, I want to say this is 25 Celsius. This is probably like 38 Celsius. So when you're doing an absolute temperature like this is only a temperature change of 13. This is going to be really low diffusion, this T. What this does more than the heat actually affecting the diffusion of the drug is it does two things. Excuse me. It will increase circulation, right? When our body gets hot, our veins will kind of expand, they'll swell to the surface of our skin to release that heat, which also increases blood flow to that area. So with the blood moving these drugs around, the more blood flow, that's actually helping this drug be administered faster. Also, if you remember, heat increases solubility. This will allow our drug to be more soluble and absorb easier. So while yes, diffusion is slightly increased by this method, it is circulation and solubility which is actually increased by this method. It's almost never diffusion. In fact, he might have even taught it that way to be a question on the exam, to almost be a trick question. Low energy heat's not really going to impact diffusion that much. Um, the final drug delivery method is essentially using some sandpaper-like substances, moving them along the skin to kind of wreck the epidermis, and then administering drugs on top of that. Um, as you can probably imagine, most patients don't like having sandpaper rubbed on them, so this isn't used that often. So that's a lot of the wacky drug delivery physical designs. As far as getting these patented, um, these are passed through a PMA. I don't know if he's going to ask this, but a PMA is kind of the equivalent to an NDA, which if you remember, the NDA is when the FDA will approve a drug to go on the market. So an PMA is kind of the same just for a medical device. Um, this is like the investigational step. This is like the equivalent of an IND, which if you remember was an investigational new drug. This is like when a compound that might have a therapeutic benefit is discovered for the first time to be tested in humans. Um, so these two right here are kind of equivalents. Again, don't know if we'll be asked that, but I just thought it was reasonable to mention it here on the last slide. Next up, we'll talk about chemical enhancers. There's a lot of different ways chemicals can enhance absorption. Uh, I'd say one of the biggest ones are fluidization, as well as hydration. These will essentially make it so the membrane, your epidermis, are a little bit more, they flow easier, they're not as dried out. So if they're not as dried out, that means there's more pores. Uh, and like water for hydrophilic drugs to move through to get deeper in. And I wanted this to be the last point of my video, but we'll get it now. Hydrophilic drugs work the best with physical enhancers, right? Um, but in, I think I wrote this, no, I didn't write this backwards. Okay, so, but my example is backwards. But anyways, I'll just give you an example of when a hydrophilic drug would work better with a chemical enhancer. If you're increasing the fluidity uh, of a membrane, right? You're making those pores a little bit bigger with more water in them. That will help a hydrophilic drug. So this is like an instance where a hydrophilic drug actually is better with a chemical enhancer. Um, that won't help out, at least these two examples right here, right? Won't help out a lipophilic drug because they'll just move through the cells anyways. It doesn't really matter. Um, but generally, hydrophilic drugs will work better with the physical enhancers, especially things like microneedles, right? Because you are physically creating a pore for them to pass through, a new hole that they can move into the skin with. Whereas lipophilic drugs don't need that as much, right? They can already just move through the cells. So other kinds of chemical enhancers, like these lipid increasing ones, or enhancing permeation. These will help out lipophilic drugs a little bit more. So again, I kind of just gave an example of each way a chemical and a physical could help both hydrophilic and lipophilic. But just know this bottom rule here, this one I haven't read, is generally 90% of the time, hydrophilic drugs will work better with physical enhancers, lipophilic drugs will work better with chemical enhancers. I can almost guarantee that'll be a question. As far as chemical enhancers we need to memorize, alcohol, fatty acids, fatty acid esters, as well as surfactants. Just be aware they exist. Don't really need to know how they work. They are just our most common ones. So if you see a list question and it is one of these on there, it is probably the answer. What makes a good enhancer? Increases the flux, duh. It makes it so the drug will pass through the membrane more often. Inert, right? We don't want this reacting with the things around it. Reversible, kind of optional, but helpful. If we're administering too much of a drug or need to vary that rate, especially if it's something like with a low therapeutics index, it could be dangerous if they got too much. Having a reversal agent's very nice, but as long as we dose it well, it's not technically necessary. And then right doesn't make the patient irritated and pain, allergic, um, and just kind of a general rule of thumb. With that, thank you so much for watching, and good luck on Monday.